All right, so let's talk implications of general relativity. Implications. So since relativity is true, you can start writing equations that seem really strange. And you might think, well, okay, that's fun, but why? Let me give you an example. Let's say I see an object, I look at an object, and it's on a very tall hill, so tall that if it were to fall down this massive gravity well, it would have a blistering amount of kinetic energy. It's sitting here, it's not moving. Let's say it could fall so fast, it could fall theoretically so fast, it would have how much energy? Well, the fastest speed you can get to is this one right here. We're not going to talk about mass for just a second. So this would be the kinetic energy you have. And this, by the way, would not be its kinetic energy because it has that much energy sitting here. Just sitting on top of this rock, it has that much potential energy, agreed? Because it have that much energy, it has enough energy so it could actually pick up this much energy once it fell, which is theoretically possible, correct? Also, let's say I'm an alien and I'm flying by at 1/2 mv squared, but my v is the speed of light. Again, can't quite get speed of light, but so close it's hard to tell the difference. If I were to look at this object, I would say it has how much kinetic energy? It would have 1/2. It would look to me like it's going 1/2 mc squared, and I have a right to my own reference frame, so it must be true. And so if we look very carefully, the total energy of this object is 1/2 mc squared plus 1/2 mc squared. Now, since it has this much energy, the actual total energy of this object is mc squared, and hence this cute little formula we talked about a little while ago. And theoretically is what we're supposed to talk about all the time in physics. We hardly ever do, because it's not that important. In fact, when Einstein made this formula up, he said, what's interesting about this formula is if you could ever make mass disappear, which he didn't think was possible, this is how much energy would be created. Okay. Harmless formula, fascinating theoretical thing, but yeah, it really doesn't mean anything. That was true all the way up to the middle 1930s. In the middle 1930s, a physicist working in Austria, a Jewish physicist, and if you know your history, that's a particularly odd thing to say, but Jewish physicist, female too, top of everything else, wrote Albert Einstein a letter, said, I don't mean to bother you, sir, because you're Einstein, but I'm very curious about this idea you have, this E equals mc squared, to which Einstein, it's not historically so, but it's probably Einstein was saying, what are you talking about, lady? What for? Oh, yeah, that weird formula that doesn't mean anything. She said, I think I have a case of it. Now, Einstein was like, you can't. It means it's like matter disappearing. But what Ms. Meitner, Dr. Meitner was saying, was Dr. Meitner noticed that when you have something like uranium, and actually she was using heavy water, so I should probably just deuterium. Okay, deuterium's got a proton, it's got a neutron, and it's weird because that's hydrogen, but it's hydrogen with a neutron, right? Now this is unstable because there's no reason to have a neutron here at all. The proton is perfectly happy by itself, and hydrogen is the worst. So it wants to shed this neutron. When it does, that neutron becomes a proton. Now, what's weird about that is there is just a little teeny tiny bit of mass that's lost when you do this. And she noted that this particle is flying off with a tremendous amount of energy. And she asked the question, she said, is there any chance that what I'm looking at is E equals mc squared? Now, Einstein initially thought no. But then they played with the numbers a little while and a couple more correspondences, and actually they met in Paris. Again, 1930s, Einstein, Meitner, two Jewish physicists meeting in Paris, talking about nuclear physics. This is it. This is a fission reaction. And Einstein quickly realized that the math worked. And so suddenly he was confused. He realized that maybe he was mistaken when he threw this formula that, in fact, if you can make mass disappear, you multiply the amount of mass times 9 times 10 to the, well, because it's c squared, 3 is 3 times 10 to the 8th, so 16th meters squared per second squared. If you multiply the amount of mass, say 1 kilogram, that's how many joules of energy you get, which is a tremendous amount of energy. And he suddenly realized this was a tremendous source of energy and was fascinated by it. And wrote some papers on this with Miss Meitner, with Dr. Meitner involved. This led to the idea that if you could get enough of these reactions to happen fast enough, say you take a big pile of this stuff, and instead you use uranium, which falls apart easier. It's easier to, it's big metal, so you can control it. But you get it so it has extra neutrons, actually short neutrons, so it's really unstable. And then you pack explosives around the outside. And then you set off a bunch of timers on the outside, so you explode it inwards, so that uranium gets compressed to a point where those neutrons, those reactions, the neutron pops off of one of these nuclei, neutron, and then slams in another one, almost automatically hits it. And so that breaks off and makes more neutrons. You end up with a chain reaction, and you end up with something that looks like this. Kaboom! Called a nuclear bomb. And so this led to the idea of a nuclear bomb. What was frightening to Einstein that nobody else was picking up on is Einstein realized if this is true, it's true for everything. What? Oh, let's talk. Let's say you get out a flashlight. I've got a flashlight, and how a flashlight works. You have your battery inside. I'm going to go ahead and draw a battery like this. That's what's typically in your thing. You put a wire in there, bad wire to make resistance. This part has to be attached in some way to the bottom of the battery. So what happens, electrons come shooting out of here, go ripping through your wire, and then go back into here, and boom, you end up with light because it went from this negative post to the positive post, and it used up some energy to get there. Great, and we got pretty light, and so your flashlight works. Beep, 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 and you're making light. Now, what's interesting about this is Einstein was troubled. He said, but E equals mc squared. E equals mc squared. So what must happen when you make energy is you must be losing some mass. And so we get the frightening implication that your regular physics teacher and your chemistry teacher don't want to talk about, which is, hey, you're keeping track of the electrons. There's no matter disappearing, but there has to be mass. Your flashlight, while it's on, is getting lighter. It's losing energy, so therefore it's losing mass. And so what's interesting is we now have, and by the way, this has been played with enough that we now know it to be true. Okay, when you have something that has extra energy, as it loses energy, it loses mass. And by the way, that's a relative thing, right? So depending on your perspective, you might not think it's losing mass. The next person standing next to you goes, oh, that thing lost mass because it's got more, it's lost energy relative to where it is. Well, by the way, when I recharge the battery, it gets the mass back. There's no particles going in. There's no physical. This effect is so trivial, we don't care about it 99.9% of the time. What do you mean by trivial? If I have a 60-watt flashlight, which would be a very, very bright flashlight, that means it's putting out 60 joules per second, right? 60 joules per second, I put in my formula, let's say for 1 second, let's see how much mass it loses. 9 times 10 to the 16th, divide that out, oh, never mind. Not losing much mass, right? You're losing almost no mass at all. You can't tell that mass with any kind of scale that's made on a human being. This has to be an energy exchange on a massive scale for us to notice it, but it does happen. It is real. It's a real thing. And so this is an implication. By the way, it's also how the sun works. The sun is smashing hydrogen into helium. That means gaining mass, except it takes 4 hydrogens to make 1 helium. While it's doing that, it loses just a hair of mass. What does that mass become? Sunlight. And that's where we get sunlight from. It's the same idea, E equals mc squared. All right, I don't think I have enough time in this video to do the second implication. We'll do the second implication in just a moment on my second video.